Hi there, this is Professor Hank, and in this video we are going to talk about binary trees. Okay, and this video is hopefully I'm planning on launching a new series that's going to lead us into a discussion about different types of binary trees. We'll talk about a binary search tree. Okay, binary search tree, which is a type of binary tree. We'll talk about a self-balancing binary search tree known as an AVL tree, right? And we'll also, depending on how this goes, I'm also planning on having a mini video series on B trees, okay? And we'll at least look at 2-3 trees. That's my goal. That's where we're going to go with this, okay? But in order to talk about binary search trees, AVL trees, B trees, we first have to talk about a binary tree and what it is. Okay, so binary tree is a type of graph, okay, that has certain properties. Okay, so here is a picture of what a binary tree could look like. Right, if we draw an example, okay, draw a very simple one. Okay, something like this, and each member of the binary tree, represented by one of these circles here, is called a node, right? So the members are called nodes, okay? And a bunch of little properties and definitions we have to get through here. So members are called nodes, and a node can have children, okay? But they can only have 0, 1, or 2 children, okay? So looking at our picture over here, what's a child? Well, here I have a node, right, this guy right here, and this node has 2 children, okay? Here's a child here, and here's a child here, okay? And each one of those children, in turn, has 2 children, okay? Now, in this case, all the nodes have 2 children except for the very, very bottom nodes, okay? They don't have any children. But we could have the case where you have a node that has, 1 child, in this case, a left child. We could have a node that has a right child, right? Or we could have a node that has no children at all, okay? Now, a child node can have at most 1 parent, right? So here's a child node right here, right? And its parent node is the node that's pointing to it, right? So this is the parent node and this is the child node, okay? A parent can have up to 2 children, but a child can only have 1 parent node, okay? So a node that has no children is called a leaf node. No children at all, okay? It's the happiest of all the nodes in the tree, right? No children to have to worry about. Okay, now it is possible that you can have one node with no parents. One node, no parent. Okay, and that node is called the root node. Okay, and you can only have one root node in any tree. So in this picture here, my root node is that guy right there. Okay, all right. Now, a path is a series of nodes from some parent to a child, right? So if we were going to start from the root node down to the lowest leaf, or one of the lowest leaves, right, down to here. We want to start here and end down here. Then one path, or the path that we would choose to get there, that we'd have to follow to get there, would start from the root node, go to that child, and then from that child, go to that child, and then from that child, go to that child. So that would be one path. That's an example of a path. Okay, now the height of a tree is going to be the length of the longest path from the root node to some leaf. Okay, so it's going to be the longest path from a root node to a leaf. Okay, so in this case, we've got a path that started at the root, and that was 1 node there, then we went to this child here, that was 2, and then 3, and then 4. So we could say that this tree has a height of 4 if we were to look at that path right there. That path is obviously longer than going, say, from root to this node to that node, right? So far it's 4. Now, we could have also examined the path going down to this leaf node right here from root, right, to leaf. Well, that's height, or that's a path of length 4 also. Okay, so both of those, either of those would work in determining what the height is, and in this case the height is 4. So this is the longest path from a root node, or from the root node to a leaf. Okay. All right. Now, what's a subtree? Well, let me clean this up a little bit. Okay, a subtree is going to be a collection of nodes from some node all the way down to leaves, right? Not necessarily from a root node, but just we can pick some node and then look at all the nodes that descend from that particular node. Okay, so here I've got another binary tree. All right, so if I was to pick this node right here, okay, if I was to do that, then the subtree would be this guy right here. Okay, if I was to pick, say, this node, then I could say the subtree exists from that node and all its children right there. Okay, so that's a subtree. And let's see here, all nodes that are going to be added are going to be leaves. Okay, so all new nodes added to a binary tree are going to be leaves. All right, and each transition from a node to a child node makes a new level. Okay, so what do I mean by that? Well, let's take a look here. If I start at the root here, this guy right here, and I transition from the root to a child, right? Either in that direction or that direction. That means that I've gone another level. Okay? So in this particular tree, I have how many possible transitions, right? Well, if I start off at the 0th level, right, I can go to the 1th level, I can go to the 2th level, and I can go to the 3rd level. So basically this thing is going to have a height of 4. Okay, now the height of 4 is going to also correspond to how many levels. Okay, all right, and the root node is always going to start at level 0. Okay, great. So that's everything that I want to talk about in this video. So in this video, what did we talk about? We talked about what a binary tree is, and I introduced you to some new terminology, right? So describing the binary tree. So in subsequent videos, what we're going to do when we continue the series is we're going to continue this series by talking about binary search trees. Okay, so a binary search tree is a binary tree with an additional property, an organizational property, which allows us to do things like performing searches on the tree, or adding new leaves to the tree that can be done very quickly in terms of big O of log event, right? Which is an improvement over a regular old singularly linked list where, you know, if you're going to do a search on that guy, you'd have to do essentially a linear search, which is big O of n. So it enables us to, in a pointer-based data structure, allow us to implement, in the average case or in the best cases, you know, searches that are essentially binary searches, which kick the snot out of plain old linear search. Okay, great. So that's everything I want to talk about. So bring this video to a close. If you have any questions, as usual, if you're a student of mine, please feel free to shoot me an email or stop by my office hours. And if you found this video useful, please consider hitting a thumbs up. All right, got that thumbs up button. And if you thought the video sucked, well, you've got that option, that thumbs down option as well. Feel free to pick whichever one you think this video deserves. And if you're so inclined, you know, why not hit that subscribe button? Okay. All right, thanks for watching, and we'll catch you next time.